Okay, so we're starting off today by kind of looking back at where we were at the end of Friday. So after Friday's class, we ended with just this overall concept of the idea of energy movement. When energy comes in, we say that the overall energy of the system increases. The value of that energy is positive. When energy leaves the system, the overall energy of the system is going to go down. And so we say that there is a negative value to that energy. So energy in is viewed as positive, energy out is viewed as negative. Doesn't matter what kind of energy we are discussing, we all get that viewpoint in the exact same kind of way when it comes to energy input and output. Now, here's where we get into some new information. In thermochemistry, at least from a chemical standpoint, there are two primary types of energy. There is work, which is described as the force applied over a distance. And we can think of that very simply, just as simple as pushing a chair from one side of the room to the other. We are using a distribution of energy. The energy is coming in the form of work. I exhibit an output of energy as I push the chair. The chair rolls away as a result of that output of energy. Now, in chemical systems, we usually don't think about energy in that kind of way. Usually, if we see any kind of work being done, it's because there's a gas involved in the reaction in some kind of way. And so the work that we are primarily concerned with in a chemical standpoint is something called PV work, pressure volume work, where we look at, does our system expand or contract as a result of this process? And we can measure and calculate the work being done by the system using this equation. Where work, W, is equal to the opposite of the external pressure multiplied by the change in volume. And so a couple of things to kind of point out about this. First of all, anytime we see this Greek letter delta, that is going to indicate some sort of change. So delta V tells us that we're looking at a change in volume here. In other kinds of scenarios, we've already seen a little bit, things like delta E for change in energy. Now, the other thing that we want to look at here is this negative sign. Why is this negative sign there? Well, here's where we have to remember our sign conventions. If my system expands, that means that delta V is going to be increased. It's going to be a positive number. So here was my initial volume. This difference would be my delta V. That's obviously an increase. It's bigger than it was. If my delta V is positive, my external pressure has to be positive also. Positive times positive gives us a positive number. But in terms of work, positive work doesn't make a whole lot of sense if the whole thing is expanding. I don't push on something and have it get smaller as a result. I push on something and it gets bigger. So the system had to have pushed this piston up, which means that the system had to have done work in this scenario. But remember, if the system does anything, outputs any kind of energy, that shows up as a negative value. And so that's why the negative is there. The negative is there to show that when that system expands, when the PV work expands the container, it's being shown as work being done by the system as opposed to on the system. So in all things, every time we see one of these equations going on here, we're always going to want to make sure that in context, the sign makes sense. So if our calculation is yielding and showing something where the system is doing something, we want to make sure that that sign is negative. When something is being done to the system, we want to make sure that the sign there is positive. The second kind of energy is called heat. Now, heat is a consequence of the transfer of energy. And we will find that energy is always transferred from the hot object to the cold object. So if I have two objects that are at different temperatures, heat is going to tell us which direction the energy is going to flow, and temperature is going to help us to predict what that relationship looks like. So if I have an object at 90 degrees and another one at 30 degrees, we know for a fact that the 90-degree object is going to transfer energy to the 30-degree object, and they're both going to change until they reach some kind of thermal equilibrium, and they end up at the same temperature. Well, for the hot object, that means that it's going to cool down. For the cool object, that means it's going to warm up. We can calculate the amount of heat that is transferred using this equation. Q is our stand-in for heat, is equal to the heat capacity, C, multiplied by the change in temperature. Now, one important note about C. C is what is called the heat capacity. Each object, each substance, has a set value for heat capacity. By definition, heat capacity is merely how much energy does it take to raise the temperature of that substance by a degree. But there's kind of a problem with heat capacity. And the problem with heat capacity is this. Think back to the thermal energy concept that we brought up on Friday. I have the small cup of coffee and the large cup of coffee, both at the same temperature. Even though they're at the same temperature, they have differing amounts of heat. Which coffee cup had more heat in it? Which one had more thermal energy? The small one or the large one? The large one. Yeah, the large one has more heat, has more thermal energy because there's more of those hot coffee molecules compared to the smaller one. Well, the same thing happens here. If I have 2 cups of water that are at room temperature, one's big and one is small, the big one's going to take a lot more energy to heat it up than the small one is. And that's a problem overall with heat capacity. There's no standardization. There's no way of comparing directly one object to another, because if they're different masses, if they're different volumes, they're going to require different amounts of heat to raise their temperatures. And so for that reason, we don't see this particular equation used very often. What we see is this equation has a cousin, and that cousin allows for one other factor to be introduced. So heat capacity tends to only be used in very specific situations. At the end of today, we'll talk about one of the specific situations, the bomb calorimeter. For most other situations, we're going to use something called specific heat capacity, or just simply specific heat. And what specific heat tells us is it gives us that heat capacity value, but it brings it down to the gram level. This is the amount of energy that it takes to raise the temperature of 1 gram of silver by 1 degree Celsius. This is the amount of energy it takes to raise 1 gram of Pyrex glass by 1 degree Celsius. This is the amount of heat it takes to raise 1 gram of wood by 1 degree Celsius. And so a couple of important things that we want to draw out here. First of all, specific heat capacity does vary by substance. And it also varies by phase. And by phase, I mean phase of matter. So if I'm looking at a sample of lead, the specific heat of lead is 0.128 joules per gram degree Celsius. Now that specific heat applies to any sample of lead that I could possibly find, so long as the lead is in the solid phase. If the lead is in the liquid phase, completely different value. The heat capacity, the specific heat of water is 4.184 joules per gram degree Celsius. But again, that applies to water in the liquid phase. If I'm looking at steam, it's going to have a different specific heat. If I'm looking at ice, it's going to have a different specific heat as well. Now, because our specific heat is put to the gram, we still do need to know how much of the substance that we have. So that's why this equation does have that mass factor in there. Now, in the lab that you're going to do on Wednesday, Thursday, we're not going to actually deal with masses because we're dealing with solutions. We're going to deal with volumes. And we're going to use a version of specific heat that standardizes to the milliliter instead of to the gram. But the idea, the concept is essentially the same. The only difference would be instead of mass times specific heat times change in temperature, it's going to be volume times what's called specific density, which combines specific heat and density together, times the change in temperature. Slight little micro wrinkles there. Overall concept's exactly the same though. Now, some trends here, some things that we ought to notice. When it comes to looking at heat values, one thing that we should notice is that metals have pretty low specific heat values. If I go back to this previous slide, the things that were metallic, lead, gold, silver, they all had relatively low specific heat values, which should make sense to us. If I have a low specific heat, that means that it doesn't require very much energy to get it to heat up. It also means that it doesn't require much energy release to cool it back down. And if you think about the kinds of things we use metals for, it kind of makes sense. Metals are good conductors of heat. So if I want to boil a pot of water and not have it take 6 years, I'm going to use a certain kind of pot that has things in it that have low specific heat values, so that as the hot plate or the stove heats up the pan, heats up the pot, that heat goes directly into the water. It doesn't get trapped in the metal. The metal literally acts as just a conductor. It passes through. Which also is really important because when I want to be done cooking, I want it to cool down pretty quickly. I dump out the water. I run the pan under cold water. It doesn't take more than a few seconds to get it to where I can touch it and clean it. Also really important. If I make comparisons, nonmetals and water, I can see that as I go toward water, my specific heat values start to get higher and higher, which makes them less and less likely to change temperature, which is one of the reasons why it takes forever to boil a pot of water. Because if I've got 4 gallons of water or whatever I'm trying to boil, it's going to require a lot of energy to get that to increase in temperature. And so the more I have, the longer it takes to boil it, and it's already requiring a good bit anyway. One other thing that we need to consider here. Heat and work often work together, and we'll get into that in just a second when we talk about the first law. But what we also want to look at is the fact that heat and work are considered path dependent variables. Since they are considered path dependent, we have to remember what that means. On Friday, we defined the concept of a state function. That is something measurable that we could determine based upon just simply the before and after, and not necessarily what happened in between. So we talked about the idea of 2 hikers on a mountain path. One climbs up the face of the mountain itself. The other one takes a trail. They both end up at the top from base camp. In terms of elevation, they both climbed the same amount. but obviously their pathways were very different. And the amount of exertion that they put in was very different. The amount of technical skill and know-how was very different. But the end result was the same. They started at base camp, they ended at the summit. Heat and work are not like that. Heat and work are path dependent, meaning it matters very much what happened in the reaction to get us there. Heat and work are also exchanged from system to surroundings and vice versa. What's important to note here is that any change in heat or work is met by an equal and opposite change in the surroundings. So come back to this concept of me pushing this chair around. As I'm exerting work on the chair, I'm referring work, so I've got a negative W. The chair, as part of my surroundings, has a positive W. Because all the work that I'm putting into it is going directly into the chair. Not a drop more, not a drop less. If I were doing heat exchanges are even and opposite. Any heat that is exchanged into the system had to have come from the surroundings, and vice versa. So what we get here when we look at heat and work individually is we get a whole lot of net zero effects. Yes, the system might bring in heat, or the system might do work. But that heat and that work has to go somewhere, has to come from somewhere. And so if the energy of the system goes up, that means that the energy of the surroundings had to go down to compensate. All right, before we get into kind of the main point of today, let's do a practice problem here and just see if we understood the first concept. So I've got 50-gram samples of each of these four substances: antimony, arsenic, barium, and beryllium. 50-gram samples of each of these, they're all starting at exactly 25 degrees Celsius. I give each of these substances the same amount of heat. If these are the final temperatures, which one of these substances has the greatest heat capacity? So give you about 30 seconds or so, maybe a couple more to get logged in. You already answered, don't bother trying to answer again. You've already got your response in. Just reset itself here. All right, let's talk about it here. So logically speaking, there are probably only two answers that make sense: the high and the low here, because they represent the two extremes. The middle two answers, I don't know how we could logically come up with them without doing some kind of calculation, and you don't need to do a calculation here. So what it comes down to is, again, what is the idea of heat capacity? Again, heat capacity is how much energy does it take to raise that substance's temperature by a degree. Now, since we have equal amounts of all of these substances and they all started in the same place, it comes down to which one changed the least in temperature. because the one that changed the least in temperature must have required the most energy to change temperature. And since that's what heat capacity is talking about, that's how we would end up with barium as our answer here instead of anything else. Barium only changed by 11 degrees. All the other ones changed by more than 100 degrees. So we added a decent amount of energy to them. But barium changed the least. Okay. So here we are, kind of to what we've been building at for 2 days now, the first law of thermodynamics. Now, before we get to the actual telling of the first law, let's define some terms here so that we're all on the same page. So we know what thermochemistry is. Thermochemistry is the specific application of the study of energy in chemistry processes. Thermodynamics is a broader study of energy to a variety of systems. Now, primarily, where we see thermodynamics the most often is in the physics and engineering kinds of realms. That's where thermodynamics has kind of the most opportunity to have the greatest application. Now, in chemistry, there is a branch of thermodynamics specifically related to chemical reactions. And thermochemistry is part of that study, but there's also a broader study that leads out to more than just heat energy, which is what we're focusing on, to other types of energy. And that exploration gets a full kind of build in Chem 106. So for those of you that are taking Chem 106 next semester, you'll see thermodynamics pop up again as we take these concepts of heat and we start to build them toward other kinds of energy distribution inside of chemical systems. And eventually what that will lead to is when you start to apply the principles of thermodynamics to redox, that's called electrochemistry. And that's where you get into batteries and other kinds of electrical systems related to chemical reactions driving the electricity. So we're getting kind of a first taste of it here. For those of you moving on to the next step, you'll see a lot more of it in the next semester. Here's our first law. Our first law is kind of twofold here. First of all, we get ourselves an equation here, and this equation links together the three types of energy we've talked about thus far. We've talked about the idea of internal energy, delta E. But now we can see that in terms of heat and work, internal energy is simply the sum of those two, heat plus work. And this is applying to the system primarily. So the change in energy of the system is equal to the heat of the system plus the work of the system. And all of those energy units are going to be in joules or kilojoules or the like. We can kind of summarize the first law with this equation right here. It says that the total energy change of the universe is equal to the heat of the universe plus the work of the universe, which is equal to 0. Now that's a long and complicated way of basically describing the law of conservation of energy. And that's really what the first law of thermodynamics is. It's the law of conservation of energy in a reaction system, in any kind of system, energy can neither be created nor destroyed. And so if we come back to this slide that we kind of jumped over here a second ago, we see that playing out. Any heat change in the system has to be matched by an opposite change in heat in the surroundings. Any change in work on the system has to be matched by a change of work in the opposite direction for the surroundings. We already kind of talked about energy being zero sum here if we look at it from a universal standpoint. Remember, universe means system and surroundings together. Often we just talk about the system because that's what we're usually interested in. But if we consider both together, that's when our law of conservation makes sense. That's when we can actually see a direct application of that law of conservation. All that we've really done here is we've put some names to it. Heat and work. Heat is conserved. Work is conserved. Both together are conserved in any kind of reaction process. And so before we move on to an application of this, I just want to pause for a second because this is a kind of a heavy hitter concept. We've been building toward this for 2 days. Does anybody have any questions about it before we start moving into how we might use it to talk about other things? All right, so the first application that we're going to talk about is something called a constant volume calorimeter, otherwise known as a bomb calorimeter. Now, why is it called a bomb calorimeter? Well, if you understand kind of what a bomb is usually a chemical reaction encased in some kind of vessel that has a fixed volume. And the way that it works is basically the pressure inside of that bomb, if it were a bomb, builds to the point where the container can no longer contain it, and it ruptures, it explodes, it does a whole bunch of damage. Well, we're doing the same kind of thing in bomb calorimetry, except for without the massive explosion and severe damage and carnage and all of that other stuff. In a bomb calorimeter, we have a two-chamber system. We have an exterior chamber and we have an interior chamber. The interior chamber is what actually houses the chemical reaction. Usually with bomb calorimetry, that chemical reaction is some kind of combustion reaction. Most often, it's a food product that we are encasing in there. So we are measuring the caloric content of peanuts. So we put peanuts inside of here, shock them with electricity to get them to burn, and then measure the temperature change in the calorimeter itself. Where a bomb calorimeter can be really useful for us is because it is a fixed volume, we can throw out the idea of work. Remember, work in chemistry is PV work. To have PV work, we have to have a change in volume. Volume is being held constant here, so there's no change in volume. So internal energy comes down to just being a measurement of Q, not of anything else. Now, there's one other important piece here that we need to recognize. In most calorimetry experiments, not just bomb calorimetry, but also other kinds of calorimetry, the system is usually not a part of the calorimeter itself. What we're taking the measurement of temperature on for this delta T is the water that is surrounding this system, surrounding that interior jacket. Because of that, we are actually measuring the change in temperature of the surroundings, not of the system. But this is where our first law of thermodynamics can actually be used. It can be handy here. Because since we're looking at the first law of thermodynamics, we know that any change of heat that happens in the surroundings is going to be met by an equal and opposite change in the system. So if I can calculate through this heat capacity and this delta T, the heat that went into this chamber, I know based on the first law of thermodynamics, all of that heat that went in here came from here. So I just use the fact that it's equal and opposite to my advantage. This is going to go up in temperature, which means that its value for Q is going to be up. It's going to increase. Which means that the reaction itself actually had to have released energy in order to do that. And so if we are interested in the internal energy change for that kind of a system, keeping that in mind, that's why the negative is here for the heat of reaction. I can use this kind of equation to figure out the value of Q. I can also use this kind of equation if I divide it by the number of moles of reactant. I can get a molar energy change, which is kind of the most often used form. All right, let's finish up today with a review question. And then finally, the stoplight. All right, with our first law of thermodynamics, so delta E is equal to Q plus W. If Q and delta E refer to the system and W refers to the surroundings, which of these four statements is true? So the trick here is, since W is referring to the surroundings, then that means that the W of the system is going to be the opposite of that. And so if I substitute, what that means is that it's delta E is equal to Q plus negative W. And so solving by adding W to both sides, E plus W is equal to Q. So letter A would be the correct answer there. So yeah, don't, C is a nice convenient package because it's the first law, but since the three variables are not all talking about the same thing, we have to get them all on like terms before we combine them. And so that's why A ends up being correct there. All right, on your way out, make sure that you answer the stoplight question. And then on Wednesday, we're going to start expanding this out to talk about a general concept called enthalpy, which we'll also use to get into more stuff with calorimetry and some other calculations as well. Have a good day.